invitation. And also would like to thank Professor Lee for All right, thank you very much. Well, thank you for coming to this beautiful conference, beautiful location. Again, I'd like to thank the organizers and Professor Park for the invitation, and also Professor Lee for giving a nice review before me on one part of how to pattern a substrate. My talk today will be on flexible displays and roll-to-roll printing techniques, current status and future prospects. Basically, this is the research that was done in my group in collaboration with some of our collaborators in the US and overseas. And again, I am from the Chemical and Materials Engineering Department, as well as from the Flexible Display Center at Arizona State University. So I'd like to thank first the collaborators and funding agencies, my team members, some of which you might recognize. Sean Shaheen is now one of the leading pioneers in the area of organic photovoltaics. He is at the National Renewable Energy Labs. There are many other people you might recognize their works after they left the group. In our group, we work not only on making devices, we start with some basic understanding, then we build on that to foundational technology like solar cells, printable organics, development of moisture barriers, transparent electrodes, and we integrate them into systems. And the group is basically working on future nanoelectronics, photonics, and bioinformatics. And this is our vision for organics and hybrid devices, is someday we will be able to integrate them into a flexible, smart system that has the display as well as the memory elements, the bio detectors, and everything is located in one unit. So if you remember printing started back in 1435 or so by Gutenberg, but before Gutenberg the Chinese and the Egyptians also worked a lot on printing, but this was basically the first high throughput printer in 1435 by Gutenberg. Now, since Gutenberg, we are now at printers that can print at the speed of cars, basically. You have a rolling around, and your newspaper is sometimes printed at a speed of 30 miles per hour, about 40-45 kilometers per hour. In our case here, I'm going to talk about inkjet printing, as well as some of our roll-to-roll based printing, including gravure and screen printing. I will be very brief. I'll show you results, and I will not talk much about the science behind this. If you have questions, you could ask about the science or see me at the break. We use a slew of inkjet printers. This is a HP printer that we buy from the market, and we break it, modify the mechanism so we can print not only on flexible substrates, but also we can print on silicon wafers, glass, and whatever substrates you have, including textile. We take the cartridges here and put them right here. This is the cartridge of an HP printer. And then we build the electronics to drive the cartridge, because here you cannot drive the cartridge at will. There is a fixed drop size that comes out, and you cannot change that. In our case, we build the electronics and put wave generators, and we can basically at command get any drop we want. We also have the piezoelectric based inkjet printers, from small size all the way up to the Lightrex machine that is about 7" by 7" substrate capability. So if you're not familiar with inkjet, it's very simple. You take the light emitting polymers and you put them inside the cartridge, and you print just like you're printing on paper. You print the red dots, the green dots, and the blue dots, and these sub-pixels form one pixel here, and that forms the whole display. It's as simple as that, although there is a lot of challenges and science and technology that went behind preparing this kind of achievement. Our case, we're not going to print red, green, and blue like you saw here. We're not going to do that. We are going to take a conducting polymer, put it in the inkjet, and then print the polymer and pattern it at will. There has been work that has been done in this area. However, it was not printed on top of a plastic or insulating surface. It was normally printed on top of an ITO. In our case, there is no ITO. We are patterning this conducting polymer directly on plastic or glass. So by using that system I talked about, we can print dots, we can print lines, and we can print layers. We can adjust the chemistry of the ink and get either concave layer or convex layers or any other shapes that the ink chemistry would allow us. And this has a ramification in solar cells as well as in light extraction. That is very important area right now in OLEDs. And we can adjust the frequency of our printing method and get a continuous layers that uniformity of which are, in my opinion, unprecedented. This is just an example of what we have got. We could control the printing. We can get single modes of P-dot. You could see by controlling the chemistry of the ink, we do not allow this dot to overlap here. So by surface tension means the dots stay separated. So you could adjust the chemistry again and make them overlap. So you have bimodal distribution of P-dot. And every two dots, by adjusting the frequency of the printing, you allow them here not to overlap at all. And that you could build eventually for solar cells. This would be an application that we are working under California support, where we increase the light into the solar cell. That way we increase the absorption and thus the efficiency. For OLEDs, this same structure could be put on the other side of the substrate and extract the light out of the substrate. So here we're marking the deposition by inkjet. You could still deposit, and by controlling the ink chemistry you could basically form a layer. And this again can be controlled by controlling the surface tension of the ink that you're printing. Well, let me skip this because here it's similar. When we print, every time we print, since we're trying to demonstrate the principle here, we're not making devices that the companies will use. What we do everything in atmospheric conditions, and we bake the P-dot PSS is conducting polymer. We bake it at 110 degrees C for 2 hours. So you could see that we do include some surfactants to modify the chemistry, the wetting, and then the glycerol here is put in order to enhance the conductivity of this polymer, because it allows for some adjustments of these chains in certain areas and increase the conductivity. This is here the thickness profile. This is very simple. What you do, you go to PowerPoint and you build these colors from PowerPoint. And PowerPoint is based on luminosity and hue colors. So this is very easy to build. And by doing so, this is the printing that we achieve. So here, the white is no printing. Then we start printing a bit and more and more and more until we get a complete coverage. And we measure the thickness of these separate layers. And for the complete coverage, that is complete black printing. So here, the computer is telling the nozzle to print until you cover the whole surface with P-dot. And we measure the thickness of these layers, and we could see that, as you might expect from common sense here, that the darker the colors, the thicker the substrate. So as you go down in color, the thickness decreases. So this is not the luminosity for LEDs, this is the luminosity of this ink basically from PowerPoint. If you compare this achievement here to spin coating, and we tried our best to maintain the thickness as much as close to the spin coating thicknesses. Since spin coating is really an established technology, and if you know the ink viscosity, you know the speed of the spinning speed, you could very easily predict the thickness of your final film. It is not so easy predicting the thickness of the film in inkjet. It's still a brand new application that needs a lot of studying and technology development to do in order to understand for a given ink viscosity and ink chemistry, how many drops do I need to put down in order to get a 50 nanometer. So we tried our best to maintain the thickness so we have a fair comparison, And this is what you see after we measured the sheet resistivity using four-point probe method. So they are pretty comparable. It's not much of a difference. And the roughness, however, is a little bit different. For inkjet printed films, the mean square roughness as measured by atomic force microscopy and by WICO as shown here is a little bit smoother, about half a nanometer or more smoother than the spin-coated device, and they're both processed in the same conditions at room temperature, at room environment and 110 degrees C drying conditions. So we made the OLED, so we spin-coated the P.PSS, and on other substrates we inkjet printed the P.PSS, and then deposited TPD rubrine for yellow emission here, then ALQ for electron transport, and the final thickness of 300 nanometers for magnesium silver as a cathode. And on some substrates we had ITO, no P dot, and built the same structure and just for comparison. So here you see ITO devices, then spin-coated devices without any ITO, and inkjet devices without any ITO. And as you might expect, ITO has a much lower sheet resistivity, therefore it can allow for a given voltage much higher currents than what you could see for P dot, either on spin-coated and inkjet. Now, if you go down here, I'm going to skip this for the interest of time. Just compare the three quantum efficiency performance. You could see that indium tin oxide, since it allows higher currents at high voltages, it allows therefore much higher Joule heating, which degrades the device pretty rapidly. Therefore, if you compare the three performances, inkjet comes on top. It's very flat performance, even up to 20 volts. In quantum efficiency, and that's what you need in your device. You need it to maintain the quantum efficiency, especially the drive voltage as time goes by, and this is we're testing now. And you can see here, this is the inkjet printed device. There is no ITO here, and this is just the shape we got from PowerPoint, and we printed it, then deposited the emitting layers and the transport, and you got this pretty easily achieved with no hard labor at all. Now, that was one way to pattern substrates and pattern structures. The reason is it's not necessarily for high resolution display at this moment. We're doing this. The market for lighting and for consumer products is about 25 times more than displays. So there's a lot of interest by the lighting industry as well as consumer products in making logos, security tags, and things related to that. And lights, solid state lights, is a huge market, much bigger than displays, and they're all after the cheapest way that you could sell them the device. Okay, and this is perhaps the most economical way to make patterns without any mask, and it's not a contact method, it's all non-contact lithography, because the inkjet doesn't even touch your substrate, it just gives you the drops. Now in this method here, we are doing something unique. What we do, we take a roll-to-roll, basically plastic substrates that are coated already with P.PSS. Before we were printing P.PSS, in this application, we bring the substrates, they are donated to us by AGFA. They are like miles and miles long, they sell more than 30-mile long substrates. But they give us the rolls, and also they cut them, they're very nice, they cut them into European size paper so that we could feed them in the inkjet. So this is plastic PEM basically that has P dot coated on it via roll coaters. The P dot PSS is about 150 to 200 nanometer thickness. So we take the sheets and put them in the inkjet printer. We take the cartridge and clean it out, but HP gives us clean cartridges already, so that helps a lot. And we put an oxidizing agent in here. So in this experiment, we're printing oxidizing agent on top of a plastic that is already been coated with P dot. So once you print the oxidizing agent on the P dot, you process it just like you process semiconductor wafers. You wash it with DI water and dry. And that's all you have to do. Then later, you can put either a single layer of emitter like a polymer, for example, or multi-layers of small molecules. It depends on your application. There is no further patterning whatsoever after the printing of the oxidizer. So you could take a picture and print it just like you print ink on paper, and then later on do the processing, wash it out, and then put everywhere the light emission and then the cathode, operate the device, and you will reproduce the details of that picture or image that you printed. Before I go show you some images, you can map out any sheet resistivity that you want for a particular application. The reason we did this is in a sense, it's a combinatorial deposition using inkjet. This is using the yellow, magenta, and kaon, and I think this is magenta and kaon. I always get these colors confused. But we put DI water in this chamber of the inkjet, and then we put a bleach like sodium hypochlorite in this chamber, and then we start mixing these on the substrate. So we're doing chemistry using inkjet right on the surface of the substrate. Of course, you can't deposit the bleach first with the inkjet. You have to deposit the water, otherwise the bleach will eat out the whole P dot on the substrate and render it extremely insulating. So these are about 5 to 10 picoliter drops. That's how small these drops are coming out of the nozzle. And we allow the mixing according to a color code. We have all these color codes, as you can see here, 100% for water. And then we start changing the printing density of the sodium hypochlorite. And we can build a library according to this color code that you can get from the PowerPoint. And you could build a library of sheet resistivities. The reason is very simple. When you come and tell us, I want you to make in this small area on the micro scale or in the mega scale if you like, I want it to be 300 ohms per square, but right next to it I want a smooth transition into 1 mega ohm per square. We can do that with inkjet. There is no way you could do it with any other technique that is known today, at least with relative ease as inkjet. So with that said and done, you could see that this looks like they're scattered all over, but if you put your eye on the sets, set by set, you could see a linear progression for 100% water, and then variation in the density of printing of the hypochlorite. You could see a linear progression, and that's what you expect from sheet resistivity. So we can go from this is the 0, no printing at all, so the P dot is as received, it's about 300 ohms per square. We can go from this, and every time we print any of these points, or the points I'm not showing either there because there's millions of these things, we also print this point here just for reproduction, just to make sure that the processing is not giving us the result. It is really the printing process that's allowing us to change this sheet resistivity in a linear scale, as you can see here. So you can take, for example, these maps and a photo of Professor Alan Heger, who was one of the Nobel Prize winners for conducting polymer in 2000, and then you could print these with oxidizers on top of the substrate, wash it out, and this is what you should see if it works. There you go. You see the map of Tucson, the sunflower, and then this is the picture of Alan Heger. The reason with these bends, and these are dust particles from our processing in the room environment. We're not doing this in a clean room. And then this bend here is the student, when they did this, they did it straight on the plastic substrate without putting a backing. When you spin coat, substrate bends, so you see these comets like so. But you could see that you could get extremely good resolution with this, and we have done this in infrared as well for security reasons, and that also is reproducible. You could see the grayscale with the dark hair that is left on the beard here, the suntan is reproduced, and also the scorpion back, which is really grayscale, reproduced very easily. And this is this, and you can see also the dust particles here from the spin coating of the light emitting polymer. So in all of these, the image was printed with the inkjet. It was scanned and printed, and then later we spin coated either the polymer single layer or 2 layers of small molecules. We did this also on paper, and these are the first application of large size OLEDs, or OLEDs for that matter, on paper. We did this way back in 2001 or so, and this is 4-inch by 4-inch substrates. If I may spend 1 minute just quickly to say what's happening, we think that the P dot is degrading in the following manner. When we do FTIR, we see some new peaks here for these type of bonds generating in here. But more importantly, recently we did, I'm going to skip the FTIR here, recently we did near-edge X-ray absorption fine structure spectroscopy, and we saw the growth with this is here the untreated substrate, so there is no oxidizer, and as we increase the oxidizer, going down to completely oxidizing, so here we put 100% oxidizer, we see the growth of carbonyl bonds, and carbonyl bonds are well known to trap charges. So they decrease the mobility, and therefore they turn the P dot from a conductor into a complete insulator as the density increases in the carbonyl bonds. Now the surface roughness of these films, as you treat them with the oxidizer, the more oxidizer you put, going from high brightness basically, so white as received, all the way up to complete darkness. Here you could see that the RMS is decreasing. So there is some sort of washing out the P dot from the substrate to smooth the substrate out. Now the question was to Professor Lee before about the interest in can these be used, can these type of machines roll-to-roll be used to pattern small features, and we believe you can, and we were actually the first group back in 2000 to show that you could use these gravure type. This is a small research scale one. It still takes a room size. If you see the one in industry, it takes a whole building size. And you could really use these type of printers to print micro features down to 1 micron if you have somebody that can make the head to print these things. I'll show you just what we did in this with VTT Electronics. We were able to print, as you could see here, 100 micron dots over a roll of film, and with root mean square roughness 1.5 nanometers, and the thickness is 20 to 30 nanometers. This is unheard of with a high-speed printer, and they are very, very nice and uniform. These edges can be taken care of by adjusting the viscosity. You can print complete layers by adjusting the size and the ink viscosity. You can print lines of polymers, and you can print dots of polymers. And when you put your light emitting layer, or you print a single layer, you could see light emission from these on plastic here. We did it on roll-to-roll plastic. So you can use patterning, high-speed patterning, to print micro features also, and for OLEDs and organic electronics. We were also the first group in the world that used screen printing to print OLEDs. And then the first time we sent this back in 1999 to be reviewed, the referee thought we were crazy because they couldn't believe we can print 90 nanometer thick layers. Later on we were able to print 10 nanometer thick layers with uniformity better than the spin coating. So this is here, screen printing is very easy. It's like a mosquito mesh, and these are the openings. You force the ink through here. So there's a lot of engineering and art that goes into this, but let me show you what we did quickly. We printed the triangle. It's about 1 inch in height, triangle here. We printed it with screen printing, and on top we deposited ALQ all over to differentiate, to see if the screen printing is really giving us patterning or not. If it's not, you should see color coming out from all this rectangle here. However, the color comes only from the triangle that we printed. At low voltage it looks much better. At high voltage the light starts guiding inside the device, and that's why you see this diffusivity here. This is not necessarily from ALQ, and our camera doesn't do fair justice to this because it filters out the yellow a lot, but you could see it here at low brightness, 3.4 volts only, and this is screen printing, right? This is the traditional printing technique for soccer jerseys and for many other applications. This technique could be very useful in printing organic light emitting diodes that have a wide spectrum for solid state lighting, and this is about 2-inch wide light, about a cell phone application basically, that was printed in our lab. It's a single layer organic white light material. We can adjust the color. You can go white, yellow, and any color very easily by doping these organic materials with a particular dye or talking to a chemist and have them change the structure a little bit. We were also, back in 2001, this hasn't been published yet because it was funded by a company. This is the first demonstration of 100 nanometer thick layers on textile that emit light. They were both screen printed and inkjet printed. And then the light is coming through the textile, not through a transparent electrode. So the textile has a roughness. You could imagine the roughness of a shirt. It's extremely high, more than 100 microns sometimes. In order to build this 100 nanometer thick device on top of a 100 micron rough surface, you have to do a lot of surface engineering to make it work. And there's still a lot of challenges. So here, if I jump to a new area, we started in 2000, and it was funded by Canon originally, and they forbid us from publishing. Until recently, we were allowed to send a publication in because the patent came through. This is an area where we're trying to develop nanomaterials that allow the emission eventually of a single wavelength from a single entity. And as you know, small molecules, you can purify them to extremely high purity. They become very expensive, but also you need to deposit them in vacuum. You cannot deposit small molecules directly from liquid processing. Polymers, on the other hand, you can inkjet print them, you can spin coat them, so that is good, but purifying them is extremely difficult. It's impossible, actually. And that's why polymers, this is one of their weak attributes at the moment, is the purity doesn't match this molecular purity, and therefore the device performance isn't as strong, as long-lasting as the small molecules. So would it be possible to find a material that takes the attributes of processability from the polymers and the attributes of purity from small molecules? And then we developed these materials. These materials have extremely high TG compared to their original materials. Let me show it down here, it would be much easier. What we do here, we use this siloxane cube here, and what we functionalize, this is in collaboration with our chemists at right now IMRE in Singapore. We functionalize this with these light emitting and also hole conducting materials, and as you could see, you could connect them covalently, so there is no phase separation when you mix these things together. You can connect them covalently at all the 8 sides of the cube. And you can control the concentration of these. You can have only 1, you can have 2, you can have 3, and you can have up to 16, even though there is only 8 sides of the cube. It turned out you can put 2 of them on this bond right here for some reason that we don't understand. And this is TPD, triphenyldiamine, is very low TG material, about 60 degrees C. And when you put it on this cube, it becomes more than 100 degrees C, as I will show you on this table. We have taken all these materials. Some are used for solar cells, some are used in our labs for OTFT, and some are for organic LEDs. And you can see the oxidizole, which has a TG normally lower than 40 degrees C if it is in its very pure form. It moves up to 172 degrees C. So if you have a device made of oxidizole, or TPD for that matter, and you leave it in the car in Phoenix, Arizona, where it gets to about more than 120 degrees C inside the car when it's parked, that device will die completely. So this kind of technology, by connecting this to the cube, it increases the TG up to 172. That is very promising technology. So here also some of the materials we did. So TPD goes from a lone TG of 60 all the way to 155 degrees C when you put it on the cube. And this is what we made comparison. We made the device on indium tin oxide. The TPD cube, we call this TPD cube, was dissolved in chloroform and then spin coated. Then we took the pure form of TPD molecular and evaporated it to the same thickness. Then we evaporated on both substrates about 60 nanometers of aluminum quinolate, which is an electron transporter. It also emits green light. Then we deposited the cathode on both and connected them to the battery. And this is what we saw. What we saw is the TPD molecular material is in black, and TPD cube is in the red triangle here. And this is the current density. You could see that because of the inclusion of the insulating nanocore, in these materials, you would expect the charge to be less free to go from one place to another. So these introduce an insulating barrier basically. However, this is very much needed for OLEDs because you want to cut down on the hole current, because they originally are very high hole mobility materials. So you don't have a balance at the interface between electrons and holes to form excitons. In order to form high number of excitons, you always have to balance the electrons and the holes, because after all, light is the exciton relaxation. So this is what we need to do, and by doing so, we increase the efficiency of the device from molecular material all the way up to the cube here reasonably well. And then the neat thing about these is you could have one single molecule or nanoblock basically, and you could modify the chemistry here and include one molecule that absorbs the energy from the surrounding molecules on the cube and emit its own light. So this is a demonstration here where you have oxidiazole nanocube and you have a pyrene nanocube, right? And you mix them together and take first the absorption and the emission. You could see that the absorption of the pyrene overlaps with the emission of the oxidiazole. So anytime this absorption overlap occurs, you're going to have forced energy transfer very efficiently. And that transfer will allow the energy to be dumped from this molecule here on the cube to this cube here, and this would emit its own light. So instead of doing so, of mixing two materials, we will take this cube, this material, and put it on the same cube, and this is what we did. So this is the simplest sensor basically, or light emitter on the nanoscale. So you have here, you excite the PBD or the oxidiazole, and you will see emission directly from the pyrene. The single molecule pyrene on a cube, you see emission from it. The nice thing about these cubes, when they go in the solid form, when they are in the liquid form, the interaction between this oxidiazole, for example, and the oxidiazole on another cube, they could come very close. Because they're in the liquid form, they could be really close together, and they could be quenching or redshift of luminescence. But as opposed to molecular materials or polymeric, when you condense molecular and polymeric materials, the emission moves to the red because of this overlap. However, these materials, because they are three-dimensional, when you condense them, those molecules that you saw here do not have the freedom to come close. They can only rotate or vibrate at that around this bond here. And therefore, this is the first observation of a blue shift in the solid state of materials that are based on organics. Most materials that we see in OLEDs and other applications, they go to the red. This material here goes to the blue. And recently we were able to form whitish. It's not completely white. There is a yellow component in it still, but it is a single layer, single molecule, single structure like this. But we modified the contents here to see whitish, and that's the ultimate aim here, is to really have a very nice white that is used not only for solid state lighting, but also for displays, because you could simplify the display design. You don't need red, green, and blue anymore. You just put the white and use the current LCD manufacturing capabilities to put the color filters, and you have a similar display as the LCDs right now, with an integrated white light and much simpler design than what people do right now in OLEDs. And then my conclusion here is that I hope I convinced you that inkjet patterning, which is a non-lithographic technique, basically you could design anything on the computer and print, is going to be used very much, not just for ultra-high resolution displays, but also for low content displays and for lighting, which is a much larger market than the ultra-high resolution displays. And there is a huge effort in Europe, I am on the board of that effort actually, where they're trying to put this in consumer products. When you go to the supermarket, you see it on the shelves and other things like that. But this would be within 10 to 20 years if this area is successful. This is just the same problems as in displays. And also we are hoping to be able to build a single nanoblock or macromolecule, if you want, that emits white light by itself without the need of any other aids to do so. And then I'd like to just remind you, we are not alone. We are up against very tough competitors, and there's a lot of hype in our area that we need to watch out for. Mainly, we are competing against people here that have this still in Helsinki airport running after more than 14 years, maybe now it's 18 years, running in Helsinki airport, and it only dropped about 25% by now. And OLED is not going to last 14 years at this brightness straight operation. Okay, so there are niche applications that OLED should really learn the lessons from LCD. LCD started in a small watch, very ugly watch. I was about 1 year old when I saw the LCD watch, and I still keep one from my uncle who used to have it. But LCDs now are up to 82-inch TV by Samsung. They showed the prototype of 82-inch TV LCD. So it takes time, but the lesson is we have to start small, and it's really interesting to see that OLEDs right now are making a lot of progress in cell phones. If you don't know it, you might have a cell phone by Samsung or others that have an OLED display on the outside. Samsung recently bypassed Pioneer as the highest production of OLED-based displays in cell phones. It used to be Pioneer 2 years ago, and now Samsung is about 45% of the market share. And then comes Right Display in Taiwan, then Pioneer. So there is a lot of interest in Korea to maintain this precedence and this leadership in displays, not only in LCDs and also OLEDs. So now they're moving into including the inner display, a full color OLED very soon. Before I wrap up, I need to show you this. This doesn't emit light, it's a mock-up, but this is eventually where we're heading. We're heading to flexible displays like this, and this was the recent center that we established at Arizona State University that was funded by the US Army. It was about I think $43.7 million for 5 years, renewable for $50 million for another 5 years, to develop things like this in the long run, not just for the Army, but it will go from Army applications into civilian applications. And I'll show you some. You might not believe this, but I'll show you a big slide, and then I wrap up my talk. This here was a newspaper actually that we printed features down to 50 micrometers using a roll-to-roll. This is again is 2000, and it has conducting polymers on it. This polymer is polyaniline, and you can see it used to be much longer, but every time I passed it in the audience, people kept cutting and cutting. So I'm not going to pass it anymore. But this here has many electronic features, including transistors and cell phone pads. Eventually, the hope is you will be able within 10 to 20 years to buy disposable cell phones that you buy them, use them for a few hours in the week, then recycle, and it's like a calling card basically, but it will be a cell phone, and many other things. This particular one has a 50 micron features, a set of arrays somewhere on this in here. So I'd like to thank the many funding agencies, including Volkswagen, which funded us recently to do this. You might figure out why they want to do these things. They would like to work on placing a flexible. This is a flexible OLED, about 2-inch large, and it will be transparent. It's going to go in the windshield or on the side windshield. There is no encapsulation, and this device survived for more than 3 weeks without any dark spots. We do something to the structure I can't talk about for obvious reasons. And thank you very much for your attention.